Okay, welcome all of you to join this session. I'm Peng Cui from Tsinghua University. I'm now an associate professor in the Tsinghua, and my research interest is mainly about pursuing the common ground between causal inference and stable learning and machine learning. So in recent years, we developed a series of methods on the stable learning to address the out-of-distribution generalization problem. So I'm very glad to chair this session. This should be the last session, right? So in this session, we will have two very interesting talks, respectively from Professor Jundong Li and Professor Fei Wang. So our first talk will be given by Professor Jundong Li from the University of Virginia. So Jundong's research interest is mainly in the deep mining and the machine learning, and especially in the feature selection, graph, data mining, causal inference, and also algorithmic fairness. So I know that there is a very latest good news from Jundong that one of his papers on the causal inference just received the best research paper in the KDD this year, right? So I believe that this work will be introduced in this talk. I really expect it. So the title of his talk is Learning Causality with Graphs. So when you're ready, it's a time, Jundong.
Okay, yeah. So let's get started. Thanks, Professor Cui, for the invitation. So it's great to be here today. So today I will talk about some recent research work that is happening in my group about learning causality with graphs. So we can see that the graphs or the networks are actually everywhere around us, right? And they have been widely used to model many real-world systems. So here I list some examples like social networks, biological networks, citation networks, Internet of Things, information networks, cyber-physical systems, and many more. So generally speaking, that the graphs provide us a universal language to describe the data as well as their relations. So machine learning on graphs is a very popular topic nowadays. So machine learning has been widely used in many different learning tasks on graphs. Right? For example, we can perform the node classification, graph classification. We can perform some unsupervised tasks like community detection and anomaly detection. So although that these algorithms are quite successful, so we should be careful that the majority of these algorithms are actually performed at the statistical correlation level. So a critical limitation here is the lack of causality. So it could be possible that the predictions are made based on certain spurious correlations. So that's the generalization capability of these learning algorithms are greatly impacted. So therefore that we argue that it's very important to consider the causality when we design graph machine learning algorithms. So here I list two examples. So for example, that the first example is about molecular property prediction. So if we really want to understand the property for a particular molecular structure, it's really important to understand the causal relations between some substructures as well as the molecular properties. And in another example, in epidemiology study, let's say given a contact network among different individuals, right? So if the government or the decision makers want to practice some policy interventions, it's really important to understand which specific policy intervention could have a causal effects to the outcome of interest, such as the infection rate, right? So since this is a causal inference conference, I don't think I need to emphasize the importance of the learning causality here. So basically, in causal inference, the key question here is that we're trying to investigate to what extent manipulating the value of a treatment would influence a possible outcome. And it has broad applications, right, ranging from healthcare, recommender systems, to education, and many more. So a key question in causal inference is that we want to infer the so-called counterfactual outcome. So for example, here, let's say if we have an electronic health record of a patient, basically we have a feature vector. So let's assume that we know that the patient takes the medicine in the real world, and we observe her health outcome, right? Let's assume that her health outcome goes bad. Okay, so this is what happening in the real world. But also that in order to quantify the causal effects between the medicine and the health outcome, it's also very important to know what is happening in the counterfactual world, right? So basically in the counterfactual world that we assume that the patient did not take the medicine, and we should also have a corresponding potential outcome for the patient. So in the other words, the key question of the causal inference is that we want to answer the what if question, right? We want to reason about a world that does not even exist. So after we get the potential outcome for the counterfactual world, basically we can take the difference between the factual outcome and the counterfactual outcome. Then we can get the individual treatment effect, right? And also that if we have a lot of we have a population, so basically we can also get the average treatment effect. That's basically the expectation of the individual treatment effect. So to perform the causal inference, it's very important that we have to make some assumptions. So one of the widely used assumptions is called the strong ignorability assumption, or people also know it as the unconfoundedness assumption. So basically it assumes that all the confounders can be measured by the observed features X. And it also assumes that each instance's probability to receive the treatment, which is the true propensity score, is between 0 and 1. Okay. So here I show the causal diagram. So basically, we can see that given the feature X, we assume that there do not exist any other confounders that causally affect the treatment and the outcome Y, right? And given this kind of assumption, then we can write down the formulation of the individual treatment effect as follows. And then our goal is that we want to learn a machine learning model that can approximate the function. So the function will take the observed features as the treatment and trying to output the expected potential outcome. But still that there could be some problems with this kind of assumption. So some people argue that this kind of assumption could be too strong to hold in practice. So therefore that they also propose a weaker version of the strong ignorability assumption. So what they do here is that they relax this kind of assumption by assuming the existence of some latent confounders Z, okay? So the latent confounders Z actually can be learned from the machine learning models X, okay? But still, so here is the causal diagram. We can see that given X, we're trying to learn the latent confounder Z, right? Z will basically influence both the treatment T and the outcome Y. But still, this kind of assumption, so it could still be too strong in certain real world scenarios. So for example, let's say we only observe a very few number of features, right? So these features could not be sufficient to characterize the latent confounders. Or it could be possible that the observed features X could be very noisy, right? So in this way, that the latent confounders that we learn could not be quite informative, okay? So in the other words, if we rely on the strong ignorability assumption or this kind of the relaxed assumption, so we could have some confounding bias. So how can we address this kind of problem? So our solution is that we're trying to incorporate the graph information into the causal inference process. So as we mentioned previously, graph data is actually everywhere around us, right? So they can be actually help us to learn better latent confounders, okay? So let's take the previous example, the medicine and health outcome example. So we can see that in the previous example, the socioeconomic status of the patient could be a possible confounder, right? Because the poor socioeconomic status of the patient could limit her access to some expensive medicine, and it can also have some negative impact on her health outcome. So back to this kind of example, we can see that although the socioeconomic status of individual could be difficult to be directly measured, it can actually be implicitly represented by some social networks among the users, right? So basically, that in social networks, I think that one of the very famous phenomena is called the homophily. Basically assumes that the similar nodes actually are very similar with each other, right? So it could also be possible that they actually share very similar confounders like the socioeconomic status. So therefore, we can see that we consider both the graph information and the feature information as some proxy variables to infer the latent confounders. So here is our problem statement. So we can see that the input is that we have the observational data for n different instances, and we also have graph information among them. And our goal is that we want to impute the missing value here. We're trying to infer the missing counterfactual outcome. And the key question is how can we leverage the graph information to infer the latent confounders? So we propose a solution called the network deconfounder. So the basic idea is quite simple. It has 3 components. So the first component is that we're trying to incorporate the features and the graph information into a graph neural network component, trying to learn the representations of the confounders. And then in the second component, based on the representations of the confounders, we're trying to make use of the factual outcome as some supervision signal to learn this kind of the latent confounders. And also in the third step that we also incorporate a representation balancing module to improve the causal inference effectiveness. So the first part, if you are familiar with graph neural networks, so this is basically very simple. We actually consider the graph neural networks, GNN, as a kind of the encoder. So we trying to feed the instance features and the graph information to the GNN, and then we can learn some representations. And then in the second step, we're trying to build a counterfactual outcome inference model with the supervision signal of the observed outcomes. Right? So typically we formulate it as a kind of the regression problem. So therefore we minimize the mean squared error on the factual outcomes. Okay. And because we have instance in both groups, right? We have treatment group and we have the control group. So here that we parameterize 2 regression models by fully connected layers, one for the treatment group, one and the other one for the control group. So we can see for this kind of formulation, right? Our goal is that we only have the factual outcome. So therefore that we minimize the loss function based on the factual outcome. But minimize the loss function for the factual outcome does not necessarily mean that the error in the counterfactual outcome is also minimized, right? Because if we want to infer the counterfactual outcome, we cannot just make use of the factual outcome to do the minimization, right? So in the other words, that there is kind of discrepancy here, right? So this kind of discrepancy is also called the distribution shift problem, okay? So in particular that it means that our model is trained on the conditional distribution of the factual outcomes, but our goal is that we want to infer the conditional distribution of the counterfactual outcome. So how can we solve this kind of problem? So the solution is that we incorporate a representation balancing module, okay? So let's assume P is the representations of the instance in the treatment group, and Q is the confounder representations for the instance in the control group. So we're trying to minimize the distribution difference to ensure that their distribution are very close to each other. So this kind of distribution difference can also be instantiated by the Wasserstein-Wang distance here. So by incorporating these 3 considerations, so basically we have the loss function for the proposed network deconfounder. So we can see that the first part is for the factual outcome prediction. So the second part is for the representation balancing, and the third part is to prevent overfitting. Okay, and we also adopt some approximation algorithms to compute the Wasserstein-Wang distance and its gradient for the model training. So after we train the model, basically we can infer the counterfactual outcome. So then for the evaluation, so I think one of the biggest challenges in the causal effects learning is that we don't have the counterfactual outcome, right? So if you look at most of the papers that we have to do some simulation, okay? So here that we also generate 2 semi-synthetic data sets based on 2 social networks. So one is called block catalog and the other one is called Flickr. So in these 2 networks, that is the instance are the bloggers or the users. Okay, the graph are the social connections between them, and the features are the backward features for the blogs or the user posts. And also we simulate the treatment. We consider that for each blogger or for each user, if her blogs or the posts are read on the mobile devices, then the desktops, we consider the user is in the treatment group. So otherwise it is in the control group. For the outcome, we make use of the number of viewers for the user blogs or the user posts. And the confounder here is the topics of the blogs or the user posts, because the topics basically influence which device that the user's blogs will be read. And also it influences the number of viewers for the user. And the key causal question we're trying to answer here is that we want to investigate for each user or for each blogger, if her blogs or the posts are read more on the mobile devices, will it increase the number of viewers for her? Okay, but because this is a kind of the semi-synthetic data sets, we actually have a parameter that controls the influence of the hidden confounders. So this is the kappa 2 here, this parameter. So if we increase the value, basically means that the influence of hidden confounders will become stronger. So we compare this method with several baseline methods, like the methods with the strong ignorability assumption and the relaxed assumption. Okay, so we use these two standard evaluation metrics to generate that the lower the value, it means that the better the performance is. And here is the experiment. We split the data into training, validation, and test. So we compare these different methods. So generally, we have two observations. So the first observation is that we find that our proposed network deconfounder framework actually outperforms most of the state-of-the-art methods. Okay, so this is the first observation. So basically, it means that incorporating the graph information actually can indeed help us to capture the latent confounders well. And also, we find that by increasing the number of the kappa 2, basically means that the influence of the hidden confounders becomes stronger. So we can see that the error of our method actually increased the least, while for other methods that the error actually increased very fast. So this observation also validates that it is important to incorporate the graph information. So this is still about some simulated data. So next, I will also use a real-world case study to further validate why we need the graph information here. So for this particular case study, we look at the causal impact of different COVID-19 related public policies on controlling the spread of the disease. Okay, so the background is that we find that many non-pharmaceutical public policies have been announced to limit the impact of COVID-19 across the United States. So basically, we have different policies like social distancing, mask requirements, travel restrictions, and so on and so forth. And also that to help the future policymakers, right? So a very natural question we can answer here is that which policy is more effective to control the spread of the COVID-19 in a given context, okay? So specifically that we look at the causal impact of different public policies. So basically we consider different public policies at the treatment and the outbreak dynamics, such as the number of confirmed cases or the number of deaths as the outcome. So one key challenge of the causal effect estimation for the public policy here is that we need to control the influence of the hidden confounders. Okay, so in this particular example, we can see that the vigilance of the residents could be a hidden confounder, right? Because that let's say in a county where the residents have a high vigilance towards COVID-19. So the government may issue some policies to enforce some social distancing at the early stage of the pandemic. And also that if the residents are more vigilant to the disease, to the COVID-19, they may also take some proactive actions to prevent them to get infected, right? So basically this kind of the vigilance could be considered as a hidden confounder. And we need to control this kind of hidden confounder. And additionally, that another challenge here is that the unobserved hidden confounders could also be time varying, right? So for example, the residents' vigilance could be low at the early stage, but it increases when the situation becomes more severe, right? So how can we capture the time varying hidden confounders? So here that we propose to make use of the temporal information. Right? We argue that the temporal information could help us to capture the time varying and unobserved hidden confounders. Okay, so for the data connection process to study this kind of problem, that we take each county in the United States as a unit, and the treatment are different public policies, and the outcome are the number of confirmed cases and the death cases in different counties. Okay, and also to control the confounders, we actually want to connect some proxy variables to infer the hidden confounders, right? Specifically, we connect two types of information. The first type of information is about the features of the different counties, right? We want the data to reflect the confounders, such as the residents' vigilance. And additionally, that we also collect some graph information to capture the dependencies among different counties. So for example, we can look at the distance network among different counties, or we can look at the mobility flow. So basically how many people travel from one county to the other county, okay? So for the treatment, so basically that we collect around 60 public policies in the United States. And for the outcome, we look at the number of confirmed cases and the death cases, okay? So in total, we have around 400 counties in the United States. And for the proxy variables, as we mentioned, right? So the first part is the features for the counties. So we look at the search popularity of COVID-19 related keywords from Google Trends. So basically, we look at that what are the keywords that people in different areas will search during the pandemic, okay? So we consider that this kind of the features can have a better reflection about some important confounders for different counties. And for the graph, as we mentioned, we look at the two networks. One is the distance network, and the other one is the population mobility flow between different counties. And we also perform some preliminary data analysis. So we find that there indeed exists some dependencies between the outbreak dynamics as well as the graph information. So for example, in these two heat maps that we find that in general that the counties that with a shorter distance or the county pairs with a higher mobility flow are more likely to have high correlation in terms of the number confirmed or in terms of the number of death cases. So therefore that it also can provide some suggestion that this kind of the graph information could be indeed useful to capture the latent confounders. So then we formulated the causal effects learning problem based on the public policies. So this is our proposed causal diagram. So we can see the left part basically is the causal diagram we have introduced before, right? This is basically correspond to a particular time step. And then also in order to capture the dynamics, we actually look at the causal diagram at the two consecutive time steps, okay? So we can see that in addition to the causal relations at each time step, so we can see between two consecutive time steps, t and t plus 1. So zt plus 1 is the confounder at the new time step. So the confounder at the new time step basically is also influenced by the previous hidden confounders, as well as the previously practiced treatment assignment, as well as the previous outcome yt. Okay. So in the other words, to capture the latent confounders at each time step, we can use three sources of information. So the first part is we can make use of the feature X, and the second part is that we can also make use of the graph A, and then the third part is that we can also make use of all the historical information, including the previous hidden confounders, the treatment assignment, and the outcome. And then this is our proposed method. So we can see that the first part is still the graph neural network component. So if you are familiar with the GNN, this is basically the GNN encoder, right? So we actually make use of the adjacency matrix as well as the feature information to learn the latent confounders at each time step. And in addition that here that we also incorporate another matrix here. HT-1 denotes the compressed historical information. We also incorporate into the GNN modeling process. And also to capture the temporal dependencies, we also make use of the RNN module to model that how the compressed information will evolve over time, okay? And then the second part is that we also trying to make use of the hidden confounders to predict the treatment, to predict the potential outcome. And this is the final loss function. So it has 4 parts, including the outcome prediction, the treatment prediction, the representation balancing module, as well as the model regularization term. So after we optimize this model, basically that we can estimate the causal effect for different public policies by using this kind of formulation, right? Basically, we get the difference between 2 potential outcomes. So this is a detailed setup for the experiment. So we have the data across around 400 counties for the year of 2020. For every 15 days is a time period, okay? So as we mentioned that because the counterfactual outcome is very difficult to be obtained. So therefore that to help us to validate our proposed solution, we're trying to assess the impact of different public policies at different levels. we first look at it at the micro level to see which category of the public policies is more effective. And then later on that we also zoom into each specific type of policy to see that which specific policy type is more effective. So in total that we look at 3 types of public policies like social distancing, reopening, and masking. Okay, so here we list some example policies in each category. And this is the result, okay? So we can see that if the value is 0, basically means that the public policy actually does not have any causal effect in preventing the spread of the COVID-19. Okay, so we look at the data across 2020, so we have different time steps. And if the value is more negative, it means that the policy is more useful to reduce the spread. And if it is more positive, basically means that it could be harmful to reducing the spread of the COVID-19. So in general, that we have 2 observations. So the first observation is that we find some public policy types like social distancing and mask actually have a positive causal effect, right, in reducing the confirmed cases. And also some other policy type like reopening could have negative impact in reducing the confirmed cases. So in general, that I want to say this kind of the observations are not quite surprising, right? And it is also consistent with some of the existing medical or epidemiology studies. But this kind of results can actually shed a light for the policy makers in design better policies to prevent the future pandemics. And this is also the experiment about the causal assessment at the micro level. So for this figure, we actually look at the public policy in the social distancing type. So we can see that the policy type like the gatherings and the food and drink seem to have the strongest causal effect. And if we also look at the descriptions at the different states, so we can see that these policies actually powerfully prohibit the number of individuals in multiple activities, especially in some high-risk places like the indoor restaurants. And at last, that we also perform some studies to further confirm that our method can learn better latent confounders, right? Because the counterfactual outcome, basically, we cannot observe. So we cannot get a real understanding about the real causal effects. But actually, we can make use of the learned confounders to predict the potential outcome, and we can also make use of it to predict the treatment. So we can see that we compare our proposed method. So CIDR dist means that our method with the distance network, and CIDR mob means that we use the mobility flow networks. So we compare it with some variants of our method. NT denotes that we do not make use of the temporal information. And NG means that we do not make use of the graph information. And also some 3 traditional methods. So in general, we can see that our method actually has a lower error in terms of the outcome prediction and the treatment prediction, okay? So as a summary that, so for this talk, right, we actually emphasize the importance of the learning causality. It is very important in many decision-making scenarios like the drug design or public policy. And also we studied some novel problems of using graph information to facilitate the causal effects learning. So we studied the problem in both a static as well as in a dynamic environment. And we propose deep learning-based solutions to learn better representations of the hidden confounders to facilitate the causal effects learning. So for the results, we actually validate the effectiveness of our method on both the semi-synthetic data sets with the generated counterfactual outcomes, as well as on a case study about the COVID-19 related public policies. So looking beyond that, I also want to talk about some other works that is happening in my group. So for example, that in addition to use the graph information to capturing the unobserved hidden confounders, we can also make use of the graph information to solve some other unaddressed problems in causal inference. So for example, if we have a graph information among different individuals, typically that we consider that the many of the causal assumptions may not necessarily hold, because that there could exist some interference or the spillover effects on the different individuals on the graph. for example, the treatment assignment for each node could actually influence the outcome of its neighbors, right? So in a recent work that in our KDD 2020 paper, basically that we actually consider that how can we capture the high order interference on a hypergraph, and we make use of this kind of the interference to further provide a better estimation of the causal effects. And in addition to using some machine learning techniques to facilitate the causal inference, we can also using some causal-driven techniques to facilitate some existing graph machine learning techniques. So for example, we also study how can we make the node representation learning process to be more fair by using the concepts called the counterfactual fairness. And we can also facilitate the explanation of some graph classification models by using some counterfactual explanation. Okay, so this is the whole reference for my today's talk. So I will wrap it up here.
Okay, thanks Jundong for the very interesting talk. Considering the time, we only have time for one quick question. So is there any question from our audience? I see there is a question in the chat box that that's about the COVID-19 project. There might be time. Can you read the question?
Yeah. So the audience asked, may I ask a question about the COVID-19 project? There might be a time gap between the policy and the COVID-19 cases in reality. So how did you consider this problem in your research? So yeah, I think that's a good question. So so in the experiments, we consider the 15 days as a particular time step. So this is also the number of days typically that we will observe that, let's say if people get infected after 15 days, they may actually diagnose this with this diagnosis with the COVID-19. But in the experiments, we also actually try different time steps. And we find that if we further reduce the time gap from 15 days to, let's say, to 1 week to 3 days to 1 day, basically the effectiveness of our method actually increased. But actually, I think for the validation purpose and also for the practical use, we limited the time step as the 15 days.
Okay, good. Thank you, Jundong. So anybody who have further questions can reach out Jundong by email. Okay, so thank you.
Yes, thank you.